Okay, the ith moment of inertia is the mass of the ith ring multiplied by the square of the r sub I star corresponding to that ring. Now the delta m sub I is 2 pi r I star times m over pi big R squared delta r. Really don't have to read that to you, I guess, but so we're going to get 2 pi r sub I star multiplied by m over pi times big R squared times delta r, and then that's multiplied by r sub I squared, r sub I star squared, the r sub I star squared from the expression for the moment of inertia will be multiplied by the r sub I star that we get as part of the expression for the mass of the ring, so that we end up with an r sub I star cubed, so that the total moment of inertia can be written as the sum from I equals 1 to n, implicitly assuming we've got n, we've partitioned the interval from 0 to big R into n equal subintervals. We're going to get the sum of these contributions. Just writing it out, and I'll step out of the way in a second. Okay, so we're just a sum of the same thing you see here, but over all the intervals. And that's going to approach the integral. Well, the partition goes from 0 to big R, so the integral is going to go from 0 to big R. Put a line there so we don't confuse this with the subscript on the I. Okay, and the r sub i's are just going to become r. The intervals are going to shrink down to where we're just representing the value at every point. And the delta r is going to become your dr by the usual process. The 2 pi over pi, of course, is going to, the pi's are going to divide out. And we're going to get, let's do the constant terms first, 2 big M over R squared. And then we'll be integrating R cubed dr. Okay, well, I'm going to get another board up here. You can do this integral. So you should pause for a minute and do the integral. There'll be another board in just a couple of seconds. Okay, you should have done this integral. I've simply factored out the constant 2 big M over big R squared, and I have the integral from 0 to big R, R cubed dr. If you do that integral, let's get the camera up a little higher so we can see that. Okay, again, I factored out the 2 big M over R squared here, leaving us the integral of R cubed dr from 0 to R. That's a very simple integral. It's equal to R to the 4th over 4. So that's 2M over big R times big R to the 4th over 4. Now you want to simplify that, you should pause and simplify it. And it's not R here, it's R squared. You should pause and simplify this. And what you get is simply 1/2 mr squared. And I hope you simplified it yourself and recognized what you had. But that's the formula for the mass, for the moment of inertia of a disk of radius big R, mass big M. That's what we're doing after R1. Okay? Now we'll talk for just a second about the moment of inertia of a sphere. We can apply the same thinking to a sphere. There's a difference with the sphere, though. A top view of the sphere looks just like a view of the disk. This would be our ring where we partitioned R along the polar axis. This would be our typical partition, and it would form a ring in the equatorial plane, the big plane of the sphere. However, unlike a disk, we don't have a uniform thickness corresponding to this ring. The disk is flat, has a uniform thickness, so we can treat this as a constant. We can treat the density as a constant surface density. We don't have that with the sphere, because if this is the top view of the sphere, the side view looks like this. So here's our partition of the polar axis. And here's a typical interval within the partition of the polar axis. It exists on this side and this side, and if we're looking down from the top, and this is our ring, if we think of coring an apple or something, this ring is going to correspond to a greater thickness of the sphere toward the center than toward the edges. The sphere has zero thickness here, has maximum thickness up here. It's rounded in this direction, so that our side view of this picture is going to look like this. This is a side view of our ring where it intersects an axis or intersects a plane in this direction. Okay, so what we get is essentially a cylindrical shell. Now this should be familiar to you from first semester calculus. So I'm going to try to sketch this in 3 dimensions, and I'm going to pause the video while I sketch that figure. And this is sort of a stick figure diagram, but what we have is we have the ring around the top, and of course the top would be along here from the front view. If we're looking at this from the side, we just see basically a rectangle. If we look at it from the top, though, we see this ring extending all the way down, so that the region would correspond to the entire ring all the way around, and so forth. So top view is here, and that's a top view of this ring, and that ring extends all the way down, and we can see where these rectangles occur relative to this figure. And the point is then that the further this ring gets toward the outside, the less thickness we have. So if we cut the ring, or if we cut the sphere at this R value, we're going to have much less thickness. This shell, this cylindrical shell here, will get shorter, but it'll get wider. So what we need to do is we need to figure out the mass density of the sphere, and this time it will be a volume density. And we need to figure out the volume corresponding to this ring, the volume of the core sample that we would take if we cut it this way. And then we need to find the moment of inertia of this cylinder about the axis through the center, the axis that would be here or here. Now, as before, we're going to take R sub I star to be the radius of this ring, and the ring is going to have thickness delta R. Here, again, we see R sub I star. We're just looking at the intersection of this ring with the plane. And I'm not going to use X, Y, and Z, but just the plane that cuts the sphere here. And that should be fairly clear. And of course, R sub I star is then the diameter of the ring that defines the cross-section of this figure. Now, the area of the ring is, again, 2 pi R sub I star times delta R. In order to find the volume of this shell, we need to find its height, so that Well, to find its height, we're going to use a triangle, and this should be very familiar from, again, first year calculus. We're going to make a triangle here. Now that triangle is going to have one leg equal to r sub I star, another leg equal to the radius big R of the sphere. And what's the third leg? The third leg is half the altitude, or half the height of this shell here. So the third leg is going to be h. We'll call it h over 2. And using the Pythagorean Theorem, we see that h over 2 is going to be the square root of big R squared minus little r sub I squared. So we could say that if h is the height of this shell, that h over 2 quantity squared equals big R squared minus little r sub I star squared, so that h is going to be 2 times the square root of big R squared minus little r sub I star squared. So now we have the height, so that the volume of the shell, and you should be writing these things down before I do, if you can. If not, of course, you want to think about what you might be missing. But the volume of the shell is just going to be the area of the ring times the altitude of the shell, or the height, h. So the volume of the shell is going to be 2 pi r sub I star delta r multiplied by 2 times the square root of big R squared minus little r sub I star squared. And close those parentheses. Now, this is going to lead us in a minute to an integral. First, we're going to have to find the density, but that's going to be easy. We're just going to divide the mass, which was presumably big M now for the sphere, by the volume, which will be 4/3 pi r cubed. And you should try to go a little further with this before you see what comes next.